Alright, so now we're going to go over these resonance problems. And for some of these, there's just going to be a couple resonance structures, and some of them will have a lot more. Now in number 1, we see this six-membered ring. And anytime we have this six-membered ring, which we'll learn in the near future is known as an aromatic ring, there's always a resonance structure that we can draw for it where the double bonds are reversed. But in addition to that, we can draw resonance structures that are similar to the ones that we saw for many of our other examples. These pi electrons from the double bond can move up onto oxygen. This gives us a plus charge on carbon and a negative charge on oxygen. Then you may notice this looks somewhat similar to some of the previous examples that we had. We have this positive charge next to a pi bond, so we can move these pi electrons over, and that will help to share this positive charge around the ring. We get a new pi bond here where the electrons move to, and then where the carbon that lost the electrons becomes positively charged because it's now electron deficient. And we can continue that pattern the rest of the way around this ring. Get a plus charge here, and do the same thing one more time. So overall, we end up with 4 primary resonance structures for this compound. Now, in theory, there are more, but these are the ones that would be the most important. Number 2 is actually a little bit simpler, because we have just the resonance structures where the pi electrons move up onto the oxygen, and then one more where those pi electrons move over to the resulting positive charge. All right, for number 3, again, we can start by moving the pi electrons up onto the oxygen. From there, we can go in 2 different directions. And what I mean by that is that we have pi electrons on both sides of our carbon that's positively charged. So we can go this way and use this double bond. Or we can use the other alkene and go in this direction, the other carbon-carbon double bond. We will learn later on that the more formal name for that is an alkene. But on this side, we can actually go a step further, because that positive charge is now next to an oxygen, which has its lone pairs. Oxygen can donate its lone pairs to that positive charge and get us 1 additional resonance structure. Finally, number 4 of this group is very similar to the first one. We can shift the pi electrons up onto the carbonyl. And then we have 2 directions we can go. We can add in the lone pair from this oxygen, just as we saw in number 3. or we can use the double bonds from the aromatic ring. And as we did in the first example, we can just continue to move around the aromatic ring by moving the next double bond over to where the positive charge is. So those are our basics for drawing resonance structures. And this is something you're certainly going to want to practice more of. It's certainly something you're going to see on exams, quizzes, etc. in this course. Our last question on this exercise asks us that we're starting with this molecule here. So which ones are valid resonance structures? So the first thing that I'm going to do is look at the charges, because the charges always need to be equal. So our starting molecule is overall neutral. That means the rest of the molecules also need to be neutral. And if we look, we see that there's one over here where we have, no, I'm sorry, all of these do add up to 0. So that's not going to rule any of them out. So the next thing I'm going to look at is what can I do to draw resonance structures? Or which ones are valid? And if I look at this carbon here, I know that that carbon already has 2 bonds to other carbons along with 2 hydrogens. So it can't take any more bonds or any more electrons. So in structures 2 and 4, we've added more electrons to that carbon. Well, that carbon already had 8 electrons. It doesn't have any pi bonds, so it can't give any away. So there's no way that that carbon can take on any more electrons. For the remaining structures, where there's nothing as obvious as that, it becomes a question of, is there a way that we can get from one to the other? So for this first one, if I take this negative charge, or the lone pair, reform the double bond, and then shift these pi electrons back down, does that get me back to my starting material? It does, and so that is a valid resonance structure. We can do the same thing in part B. Move these pi electrons, the lone pair back, and then shift the pi electrons back onto nitrogen. That gets us right back to our starting material. The fifth one looks a little funny. But if you think about what we've done with carbonyls, the carbon-oxygen double bond in the past, where we take the pi electrons and move them onto one atom, giving us a plus and a minus charge, that's what's happened here. One of our pi bonds became this plus minus. The pi bond over here became this plus and minus. And the pi bond down here became this plus and minus. So it's an odd looking resonance structure. It's definitely not an important resonance structure. That many charges is not likely to be significant. But if the question is this a valid resonance structure? The answer is yes.